here. So I go, okay, A9 drops me into B. Okay, well, what are the 0 switches associated with B? Well, it's B10, B8, B3. B10, B8, B3. See how regular that is? You just have to figure out where where the 0 switch is going to drop you, and in terms of state, and then you look at the 0 switch row corresponding to that state, and you create the possible combinations there. So similarly, here's the B row, and I got B10. Now B10 drops me into C, so there's C14, C11, and C4. So there they all are, right there, right? B10, C14, B10, C11, B10, C4. B8 drops me back into A, so there's A1, A2, A9. There they all are. B3 drops me into E. There are no outbounds from E. Okay? So everybody see how to generate this table, I hope. It's a purely mechanical thing, right? Looks complicated at first, but once you see how the 0 switches are created and then how the 1 switch portion is created from the 0 switch side, it's purely mechanical. Now, obviously, it would not be a lot of fun for a complex system that had a lot of outbound transitions from it, right? So, but if you want to try to force simple systems to have long length transitions, and that's something you can do with this technique. Or better yet, just figure out a way to automate it. Okay, so to derive tests that achieve a certain level of switch coverage, what you want to do, again, start with the tests that you derived from state transition, from the state transition diagram for state transition coverage. Don't go back to the table. The table, once you've done the table to try to force out into the open those unhandled events or event condition combinations, that you don't go back to it. Okay, so start with the tests for state transition coverage, and then construct the switch table. Confirm that the tests that you already had cover the 0 switch columns, and of course they should, right? Because our coverage criteria for the state diagram was visit every state and traverse every transition. So if we've traversed every transition, then certainly every transition sequence of length 1 should have been traversed at least once, right? Now, what will typically happen is that not only will you have traversed all transitions once, because most of the tests that you define will end up being more than one transition long, you actually have covered higher order switches. Now, in this case, we're only interested in 1 switches, in other words, transitions of length 2. But you typically will have covered sequences that are 2, 3, 4, maybe even 5 transitions long in the course of a single test. Okay? So check to see what you've already covered. Then look at your 1 switches, 2 switches, 3 switches, whatever, however high you're going with this thing, that have not been covered. And take a test, again, existing test, or just use 0 switch sequences to get you to a state where there is an uncovered higher order switch starting. Put that switch in the test, repeat until you get to a terminating state. Again, mark the switches covered. So you got the table, highlight them, you covered them. Repeat that until done. Okay, so let's take a look. The 5 tests that had been previously defined for state transition cover are shown in the blue highlighting here. Okay, so you see we did get all of the 0 switches, plus we got a bunch of the 1 switches. See that? Just by tracing through the 5 existing tests. But there were some that we didn't get. Okay? So the red shaded cells are new ones. So we did not get A1, A1, and we didn't get A1, A2. So I can get them here. A1, 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 A2. Now notice that reuse is allowed in the sense that this guy here, these 2 here, A1, A1 covered that, And these two here, A1, A2, covered that. Even though this A1 had already, quote unquote, been used, okay? But it doesn't matter. You're not trying to cover these things independent of anything else. You're just trying to force all possible transitions of length 2, in this particular case, to have been taken. Whether they were taken as part of doing something else doesn't matter. You just want to make sure that they've been done. Okay? Here we see B8, A1, and B8, A2. So there it is there. All right. See how that works? So you continue this process until you've covered all of these guys, you see here in the red, and then you're done. Okay. And I noticed the last time I ran this course that this last test here actually is incorrect. It's missing a B3 because it ends up in A9, puts you in the B state. So this should actually have a B3 here to get you into the E state. Because remember, the rule, which we inherited from our tests initially, was you got to get to the final state to be done with the test. Okay, so I just point out there is a missing transition here, a B3 transition to get me to the E state. Okay. All right. Now, let me just mention another point here. Equivalence partitioning and boundary value analysis can be applied to state diagrams. In general, you know, any set of testing techniques can be blended together to generate tests, and you should always feel free to do that. So, for example, you think of the pay good event. Now, notice I'm showing this in a little oval here, but this is not a state. Pay good was actually an event condition combination in the diagram, right? I can do equivalence partitioning on that if I support 4 different credit cards, and I can say, well, I want to have a good payment, in other words, a processed payment that covers all 4 of the supporting credit cards, American Express, MasterCard, Visa, and Discover, right? So that would be an example of applying equivalence partitioning to this event condition combination. Similarly, I could look at purchase good and purchase bad, and I could say, well, I could do boundary value analysis on the amount, because maybe I've got some ranges defined for what's the minimum and maximum purchase. See? So I could say, well, clearly, somebody tries to make a negative purchase, then that's not right. So I want to test the negative, some big maximum negative number, and then you know, -1 cent. And then 0 is always interesting, right? So that's its own invalid here. And then 1 cent up to $9.99, assuming that $10 is my minimum, right? And then I want to test a $10 purchase and a $10,000 purchase. And then if that $10,000 is the max, then I want to test a $10,001 just overflowing the shopping cart, and then some really huge number. Okay, so that would be a combination of boundary value analysis, state transition technique, which is always legitimate and certainly something that you can do. Now, the previous presentation, the previous webinar on this topic, I discussed state diagrams, and the question that sometimes comes up is, or excuse me, I discussed decision tables, and the question that sometimes comes up is, well, should I use a state-based technique or should I use decision tables? And there are certainly cases where it's sort of a matter of personal preference. A ATM, for example, can typically be modeled either as a state diagram or as a decision table, and it's really up to you how you want to do it. What will happen is, as the number of states increases, if you're going to try to use a decision table, then you end up using the conditions in the decision table to try to monitor the states. And that gets cumbersome after a while, because what happens is that the number of conditions starts to really grow in the decision table. Especially if you're going to try to create a full decision table that shows all combinations of conditions, you start to get a lot of